Now, while we are still on the chapter of pure bending, what we are going to study next are composite beams. Now, from the name you can tell composite beams are essentially beams made of two dissimilar materials. Right? So maybe they are stuck together or held in place by one mechanism or the other. Now, until now, what the things which we have studied, locating the position of the neutral axis, calculating the stresses, the formula equals to sigma my by I. All of those were made of. We studied that they were all. We had assumed that the beam is made of one single material. So it's just a homogeneous beam made of one single material. Now, if we talk about a composite beam, and this is an example of a composite beam that we have over here. So what you see is that on the top we have the rubber portion, the blue portion is rubber, and the bottom part is styrofoam. And what I've simply done is that I've taken the rubber chunk and along the interface I've applied glue, right? So the top rubber chunk is attached now to the styrofoam over here. Now, since they're attached, right, the movement of the bottom part or the top part also affects the movement of the other part over here. Now, what we are going to see that for these beams, are the formulas we derived for bending, are they valid, right? And also if they are, then how do we now possibly compute the stresses if this beam is subjected to now bending? Are the assumptions of plane section remain plane valid? And if they are, and also how do we compute the stresses at the interfaces at the top of this beam, which is made of a different material than the bottom part over here? So this is the overall objective of this particular lecture which is there. Now you may ask that why are we studying this? Why composite beams? Why are composite beams important? Well, let me draw your attention. So composite beams are actually very, very important even for civil engineering structures. For example, there can be n number of examples of composite beams. So these are some of the examples that you see over here. Here you have a wooden beam and maybe a steel bottom part over here. This is a very common beam in wooden structures where you have a top wooden plank, bottom wooden plank, and in between you have a metal sheeting, right? And the most classic example of composite beams are reinforced concrete beams. So all the reinforced concrete structures which are made around you are all composite materials. Why are they composite? Because it consists of two separate materials. One is concrete and the other one is steel, right? Now, before we go ahead and try to understand the behavior of these composite beams that are there, let's maybe do a quick recap of what we have studied for the beams which are made of homogeneous sections, right? Now, for those beams, if you recollect what we had seen, that some of these essential formulas which are there, right? So these are the beams which are made of, say, one single material. So this is made of one single material for which we have studied these particular formulas. Remember, these were the precursors to the formula which we had derived. We had taken these and sort of taken it ahead and derived these formulas that your sigma was equals to the m times y divided by I, right? Now, to get these formulas over here, we had relied on these ones where your epsilon, remember we had derived this from that curvature formula, that epsilon is equal to the kappa times y, where your kappa is the reciprocal of the radius of curvature. So kappa is 1 divided by this rho that you have over here, and this is simply Hooke's law that you see that your sigma is E times epsilon. So you have this kind of formulations that is over there, right? Now let's move ahead that and let's see that how these formulations, or how do we derive these stresses and so on for composite beams. Now, if you take a look at a composite beam, so which you see over here, say this particular beam that you see, let's say this is made of two materials. Let's say the top one is material 1 that you see over here, and the bottom one is material 2. Right? So these are two different materials, and how do we classify that materials? How do we tell what is different in material 1 than from material 2? Yes, you got it right, that material 1 has, say, the Young's modulus of E1, and material 2, say, has the Young's modulus of E2, right? So two different materials having different Young's moduli that is there. Now, how does this beam bend? So if you just try to visualize how this beam bends, if you just try to visualize this one over here, how this bends is that we are going to have something along this. So this is the overall bending behavior of the beam, say, right? And this is the interface which also bends. So this interface is this one over here, right? But now remember that your neutral axis need not be at the interface. Well, for composite beams, the neutral axis need not be even at the centroid. When you're looking at that composite section, there is a way to transform it to the centroid, which we will see. But for composite beams, this neutral axis, so maybe I have, a neutral axis somewhere over here, right, which is this particular guy over here. So this is my neutral axis. The neutral axis need not be, for composite beams, neutral axis need not be at the centroid, because remember how we had derived that particular formula that neutral axis goes to the centroid from the first principle of statics, which may not be valid in this particular case, and we will see why, right? So this is how the overall composite section bends. So you have here your top portion that you see. This is your material 1, and the bottom portion over here is material 2. So this is the top portion and this is the bottom portion that you have over here, right? Okay, so now let's go ahead and try to derive some formulations and try to first understand that what kind of complications can happen in these composite beams, and how do we get over those complications and make our life easier. So let's go ahead. So here, so I again come back to the composite beam that you have over here. Now let's just break it down, that the assumptions which we had studied. Now I want to draw your attention again to this beam over here, right, made of two different materials. And what I have done, I have drawn these black lines that you see, which I had drawn in the previous beam also, which was made of one single material. Right, now in this beam, now if you try to bend this beam over here, now take a look at these vertical black lines, right? So if you take a look at the vertical black lines, one of the assumptions that we did previously when it was the beam, when we were looking at beams with one single material, is that your plane sections remain plane before and after bending. So that essentially led us to the assumption that your strains are all linearly proportional from the distance to the neutral axis, right? So here also you see, if I take this beam, although it is made of two different materials, when I try to bend it, right, my straight line still remains straight. It does not warp or anything. So the assumption of the plane section remains plane, it still stays valid, and that leads to the second, that leads to consequently leads to the hypothesis that your sections which were initially vertical, so your strains essentially again become proportional to the distance from the neutral axis, which is something like this that you see over here. So here if you see, so this is how the strains look like. So if this is my this is my y over here, and this is my epsilon that I see, right? So how does the epsilon vary? So here I can write that my epsilon from the strain formula equals to minus y divided by rho over here. This is what we have seen. So this is still valid. So you have a radius of curvature, that is rho, and your epsilon, and this is again, remember, this is my neutral axis over here, right? And this is again my material 1 with modulus of elasticity E1, and this is material 2 with modulus of elasticity E2. So my strains are still proportional. Now here is the catch. Now what happens to the stresses? Stresses are not going to have this kind of nice linear variation all throughout the section. Now why is that? Now because remember, from Hooke's law we know that my sigma equals, this is the general Hooke's law, not for any particular material, E times epsilon over here. Now this E, now you're dealing with two different E's that you have over here. Now suppose if I have to draw the stress strain curve for these two different materials, how does the stress strain curve typically look like? So if I have this is my vertical axis for sigma and this is my vertical axis for epsilon, maybe up to the proportionality limit, maybe my for material 1 it goes like this, for material 2 it goes like this over here, right? So this is say for material 1 and this is for material 2. So material 2 has a E2, maybe it is stiffer, so it needs more amount of stress for the same amount of strain, right? So now consider at this interface, at this particular interface that you see over here, the strains, because you have the no slip condition. So that is very important. You have no slip over here because you see over here. So at the interface there is no slip, so it is bending same at that interface. So at this interface, the strain in material 1 is same as the strain in material 2. So if I have a particular strain over here, but if I try to go and calculate the stresses, now I am going to have two different stresses. I am going to have sigma one particular sigma for material 1, which is this one over here, and another sigma over here. So there is going to be a jump at that particular interface. I'm going to have some discontinuity. So let's see how the discontinuity looks like. So if you take a look at the discontinuity, this is how the stress looks like over here, where you see this top part over here, this top part up to here is for your material 1, and this part over here is for your material 2, and the neutral axis stays intact. Neutral axis is over here. So overall you have the neutral axis, right? So this is the plot of your y versus your sigma over here, for which for the material 1 what we can write that your sigma 1, as we know, is minus e times y, e1 times y divided by rho, right? And for the material 2 I can write a similar formula, that is your sigma 2 is equals to minus, but e2 now y divided by rho. This is the generic formula based on the distance y that we have over here. So these are the two things that we see. So now you see the problem becomes a bit complex, because now here you cannot simply calculate the stresses, because now you have to have a discontinuity over here in this, especially in this particular region that you see over here. Now how do we solve this, right? How do we now calculate the stresses and so on? You can go and calculate the strains, and from strain you can calculate the stresses. So that becomes sort of a roundabout way to calculate the stresses. Now to solve composite beams and to calculate the stresses at the interface at the top and the bottom, there is an easier method that exists, and quite an intuitive method if you ask me, that is known as the method of transformed sections. And now we will see that how to go ahead and derive some of the formulations for the method of transformed section. So let me go back and go to the same thing that we started with. So we have the beam over here, again material 1, material 2, and this is my e1 and e2, and let me mark the width of the beam also for you. So let's say the width of the beam is b over here, right? So now in this beam, right, suppose if I take a small element in the material 2 over here. So again let me mark this material 1 and this is material 2 over here, and let's say in this material, and this is my neutral axis. Now let's say in this material 2 I take a small element of say area dA, right? So this element over here, let's say it has an area of dA. Now for this particular element, if I have to write the force this element exists, so let me, since it is material 2, let me write it as dF2, right? So dF2, this is the force which is experienced by the material 2 that you have. So how do we calculate the force? Force is nothing but stress times the area, right? So in this particular case, the force is going to be that your, I can write dF2 is your sigma 2, right, which is the stress in the material 2. It's a generic term that I'm writing over here, times dA. So this is the force which is over there. Now sigma 2, what did we see over here? It is this particular guy. So let me further simplify that over here. What I get, dF2 is equal to minus of E2 y divided by rho times dA over here, right? So now everything is intact. So I have written the forces in terms of the properties of the material 2, that is the E2 that you see, and y is the generic distance. Y is maybe the distance from the neutral axis to the centroid of this small rectangle that we have seen, right? Now let me now introduce a new terminology, n. So I'm going to write n as a ratio of E2 to E1, right? So n is the ratio of the modulus of elasticity of material 2 to material 1 over here, and n, since it's the ratio of the modulus of elasticity, n is also known as the modular ratio. So n is also another terminology for n is modular ratio, right? So this is the ratio of the E2 to E1. So this in turn gives me something that your E1 is equals to n times E2, right? So if I take this, if I take this one over here, or sorry, I think I wrote that wrong, so let me just erase that. Sorry, this will be E2 equals to n times E1. Yeah, now it's right. So if I take this and if I plug this guy back over here, what I essentially get, this particular formulation that reduces to minus E1 times Y divided by rho times N dA, right? So this is important now. So what do we see? And now let's say that this particular element over here, right? So this particular element, let's say it has suppose this particular length is dx, because this is the x direction, and say this particular length is dy over here. So this I can further write this is minus E1 y rho. I'm just from the dA, so dA equals to dy times dx. I'm just pulling the dy out as well. So let me go take this dy times n dx, right? So now that we have this, so what does it tell you? What does this or this one tell you over here? It tells you that the stress, since we are doing the force, we are calculating the force. So what it essentially tells you is that this force, which is taken by the area of dA for a material, for a component which is made of material 2 over here. Now if I transform this material 2 to material 1, so I have converted E2 to E1, but then with the help of this modular ratio over here, the same force, because the dF2 doesn't change, the dF2 stays the same, the same force can be taken by a material 1, because you see E1 over here, provided you have increased the area n times, right? So here you see the only difference between this and these two over here is that E2 I have changed to E1, and what was dA I have made into NdA. So the force which was taken by the material 2 can be taken also by the material 1, provided you have bumped up the area n times the original area that you have considered. And what does it mean? N times the original area, so n times dA over here. Now so what I have done over here is that I have transformed material 2 into material 1 that you see over here. Now if I do not want the height of the section to change, right? So essentially I have to keep my dy's as constant, right? So dy, because this dA is dy times dx, so I have to keep the dy's as constant over here. So the only way for me to bump up this area is to increase the width. I have to increase the dx. So whatever was dx becomes n dx now. Now why am I averse to increasing the height, right? Because I don't want the position of my neutral axis or the overall strain profile to change. I want my strain profile to remain the same. I want it to have a strain over here. I want it to have a zero strain where the neutral axis was, and I want to have a a bottom strain over here. I don't want my strain profile to change. So if my section, right, initially instead of being this, if it suddenly becomes too wide, my strain profile might change. So I am not going to change my strain profile. So without changing my strain profile, that is without altering the height of this entire section that I have, I'm only bumping the width that is there, right? So essentially, again, just to reiterate, what I'm trying to say is that the force taken by this material 2 can be taken by an equivalent transformed material 1, provided for every small element, if you are keeping the overall height at the same, provided every small element that you have is bumped up by this factor n, which is nothing but this modular ratio that we have over here, right? So this is important. Now let's see how to do that. Now here you have this particular material, right? So if we have this one, what we had was initially this dA over here. Now this is again the original section. Now I'm going to transform it to another section where the entire section is made of material 1. So you see, in the original section you had a material 1 and you had a material 2 over here. Now if you go to the transformed section, this is how the transformed section looks like. Everything is the same. The top is at the same location, the bottom is at the same location, the neutral axis is at the same location over here. Only thing what I have done, so essentially I've kept the height as the same, because you see here my y I'm not changing, I'm keeping the strain profile as the same. The only thing which I have done is that I have bumped up this width over here. So here my original width was B, the top part, which is still material 1 over here, is stays B, but the bottom part, every dx I have increased to n times dx. So the bottom part, this bottom width now becomes n times B over here. And the beauty of this is I have taken a section which was made of two different materials, that is material 1 and material 2, and I have transformed it to an equivalent section, the entirety of which is now made of material 1. So everything, the whole section is made of material 1 over here. So the whole thing is made of material 1. Now, what did we gain by doing this? What did we gain by transforming this section to material 1 over here? Well, what we gained was that now you see here for this particular case, the strain profile remains the same. I have not tinkered the strain profile. You have a top strain, you have a zero strain at the neutral axis. So let me mark the neutral axis again over here. This is NA. Strain profile remains the same. And now, since the whole section is now made of material 1 over here, my stresses are linearly proportional to the strain. So instead of having a jump, I am going to have, instead of having a jump at the interface over here, I am going to have a smooth linear line, something like this over here. I am going to have a linear line which is something like this. Right? So the entire thing is now made of material 1. So the strain is of material 1, and from the strain I have calculated the stresses over here. So this is again, this is your y and this is your epsilon, and for the entire section I can write that since I've converted everything to material 1, I can write my general formula sigma 1 equals to minus E1 times y divided by rho over here. Right? Now you might be thinking that okay, now I converted everything to material 1, and now see one important thing I want you to observe before I move ahead is that you see this top part over here, this part, this particular part, right, where it had stayed the same at this interface. So this is the interface which was there, this is the interface which you have continued. So this top portion, right, is exactly identical to this top portion that you have over here, because it was originally material 1 and you also material 1 now. Now you might be wondering that what did I gain by this? Why did I have to do all of that? Now, and also, how do I compute the stresses in material 2? How do I compute the jump over here and these stresses over here? Now, can you guess that how do I get, from here, how do I go from this particular stress to this particular stress over here? Yes, it's obvious from this particular picture as well. Essentially, what you have to do to now get back the stresses. So this entire thing is for material 1, right? Now to get back the stresses for material 2, that is these stresses over here, that is the entire material 2, all I have to do is calculate these stresses and multiply it with the modular ratio, because the modular ratio is the one which helped me to go from your material 2 to material 1. And as you can see from here, if you take this particular ordinate, this is this one over here, and you multiply with the modular ratio n, you're going to have a bumped up stress over here. So essentially, if you take this one and if you multiply with n, you are essentially at this particular, see this part I don't have to multiply with n, because here what was material 1 and I have retained my material 1 over here, but for material 2 in these sections I have to multiply the stress that I get over here with simply the modular ratio, because remember, your at this particular interfaces, this was the stresses which were corresponding to material 1 over here. So if you go to this particular point, then you have to multiply with the modular ratio n that is there, right? So so the overall summary of this, this particular figure over here is that you have to keep one thing in mind, which is very important, that after you transform the section, the stresses that you are calculating, it corresponds to one particular material, but now here again you have back transformed to the original section, that is here the top part is again your material 1, and the bottom part, not the bottom part, like from here, from this this particular interface that you see is here your material 2. Now you might be wondering that, here this preassumes, since you are seeing a bump over here, this increases over here, and since this width also increases, you're pre-assuming that your E2 is greater than E1. So when E2 is greater than E1, what essentially happens, see this N, if E2 greater than E1 means N is greater than 1. Right, so that means this n dx means it's an increasing quantity. That's why you have a bumping up of the width as well, right? So when your n, so this essentially means that when your n is greater than 1, this will cause a widening, which you saw in this particular example over here. Now what if n is less than 1? If n is less than 1, you will have a shrinking. For example, in this problem, if I was converting material 2 to material 1 over here, right, then it will be, your n will be E1 divided by E2. So in that case, I will have a shrinking. So I will have this thing as intact, and this rectangle will shrink somewhat. So if you have n which is less than 1, so you will have a shrinking, right? So to summarize, so after this entire mathematical formulation and derivation and so on, if we have to summarize that what are the steps I need to follow to solve a problem of composite beams, so let's go ahead and take a look at the steps. So the steps essentially are what we did. So what are the tips to solve? So this is the summary slide which everybody loves, right, instead of solving all those equations every time. So what do we do for this? So the steps are very simple. So first, so you have a beam with material 1, material 2, different, the strain profile is the same, the plane sections remain plane, but here you have a jump over here. So what are the tips? So the tips are, first, number 1, you calculate the modular ratio n. So n is nothing but your E2 divided by E1, or E1 divided by E2, however you want to do that. So this is the that's their first step, to calculate the modular ratio, right? What is the next step? The next step is to create a transformed section by transforming material 2 to material 1. This is what we have done over here. And remember, this is very, very important. You are keeping the height, the h, the overall height that you have. So let me maybe mark that explicitly over here. This h that you see over here, this h remains the same. This h is intact, right? This h is intact over here. So you create so only thing you are doing that is that this width that is there, right, this width is increasing, the b becomes nb. So you have created a transformed section by transforming the area of material 2 to material 1. And next is you calculate the stresses for the transformed section. So this is the transformed section over here, entirety of which is made of material 1. So this stress profile is entirety for material 1 over here, right? So next you are trying to calculate what is the stresses for material 2. So you calculate the stresses for material 2 by simply multiplying for this region over here. For these regions, you take whatever is the sigma and you multiply with the modular ratio n over here, right? And the last step is that it's not particularly a step. So now you know how to calculate the stresses for the material 2. You take these stresses over here, right, and you simply multiply with n. That will lead you to these stresses over here, and this one and this one remains unchanged. So that is essentially your last step. So that is essentially the last step, that your stresses for the material 1 remains unchanged. So again, just a quick rundown is that calculate modular ratio, transform material 2 to material 1, or if you want to do the other way, that's also fine. Is that, so typically what I like to do, I like to convert the stiffer material to the less stiff. So I take the ratio as E2 to E1, but you will see in some of the problems it might be easier to consider a shrinking. It depends on the problem, but in most of the cases, if you convert the stiffer to the less stiff material, it's easier. You have a widening. So essentially every time you have a widening, right? So and then you calculate the stresses of the transformed section for the material 1. Then you calculate the stresses for the material 2 by your back transformation. The stresses for the material 1 remains unchanged. Now a lot of these concepts are going to get clear once we do a particular example problem. So let's go ahead and dive in and do an example problem on composite beams to see that how we are going to use this, you know, these things which we did. And you know, just a word about it, that this entire, you know, methodology that you saw over here, this is known as the method of transformation. So let me just write that down. Method of transformation. Right, so here are making a transform section essential. Now let's go ahead and dive in and look at a particular problem example.